Hey, what's up, YouTube fans? So I wanted to continue on this video a little bit talking about the evolution of the limbs, right? Yesterday I made a more in-depth video on the evolution of the overall human skeleton. But in this video, I wanted to talk a little bit more about the limbs specifically, right? So obviously, in the human lineage, we became better adapted towards bipedalism, evolving arches in the feet and the big toe lined with the other toes. The feet are first like that in Australopithecus, right? And in Australopithecus, the legs first start being longer than the arms. Not in all Australopithecus individuals that have been found, right? But in the case of the Littlefoot fossil, over 90% complete Australopithecus skeleton, the legs were longer than the arms, right? This is a change that happened as our ancestors adapted to bipedalism. And then our closest living relatives, the chimpanzees and bonobos, they can move on 2 feet. They're able to, but they're just not as well adapted towards it. And creatures that are already tree climbing, they're going to be more predisposed towards walking on 2 feet, right? Because they have a more upright posture. And in early apes, I said about how there was early apes evolved a dorsally positioned scapula, allowing for highly mobile shoulders, and that still applies to us. And then early primates, I said about how they evolved grasping ability of the hands and feet and more mobile limbs. And so in primates, we get arms and hands, right? Whereas for most tetrapods, rather than having 2 arms and hands and 2 legs and feet, like is the case for us, most tetrapods have 4 legs and 4 feet. But what I said about in the other video is that that's actually not a fundamental difference, right? Because quadrupedal tetrapods like dog or lizard or elephant, whatever, they still have in their front 2 legs and feet, they have all the same bones as in your arms and hands, humerus, radius, ulna, carpals, metacarpals, and phalanges, right? And the toes, right, there's their fundamental structure is the same as that of the fingers, right? So the front legs and feet of quadrupedal tetrapods are not fundamentally different from our arms and hands. So the evolution of arms and hands does not require that it be evolved from scratch. Rather, it's just a matter of specializing the front legs and feet towards new purpose, basically, right? And before primates were more so adapted to life in the trees, our ancestors were already likely spending a lot of time in the trees. This is indicated by the fact that DNA evidence indicates that the closest living relatives of primates are the colugos and the tree shrews, and they both spend a lot of time in the trees as well, even though they're not as well adapted to life in the trees, right? It's, in the case of the tree shrews, they spend so much time in the trees that it's even in their name, tree shrew, right? And we commonly see many other creatures going up into the trees, many other mammals that are not as well adapted towards it, other tetrapods that are not as well adapted to it. Bears go up into trees, even lions go up into trees. They're much more quadrupedal, but they can climb up high in the treetops. And so, once you have a species that's spending a lot of time in the trees, they can become better and better adapted to life in the trees. And there's certain evolutionary pressures that can make it advantageous to spend more time in the trees, such as avoiding predators on the ground, like let's say if there's a predator that can't itself get into the trees, then climbing in the trees would obviously be a good way of escaping it. Also, climbing in the trees could be a good way of accessing food in the trees. So there's some pretty obvious evolutionary advantages that could come from spending more time in the trees, thus creating evolutionary advantage towards adapting to life in the trees. And then furthermore, this is something I didn't cover on the other video with the evolution of the mammalian skeleton, is that something that's distinct with the mammalian limbs, right, is the positioning. For mammals, the legs tend to be much more vertically positioned, whereas in reptiles and in salamanders, we see the legs are much more so horizontally positioned, right? So if you look at like a dog or a horse, an elephant, a bear, a cat, these various mammals, what you'll commonly see in mammals is their legs more so positioned under their body and their body elevated high above the ground, right? But that's a more advanced form of leg positioning. That's not what we see in the earliest tetrapods that show up in the fossil record. So, you know, in most reptiles such as lizards and crocodiles, alligators, and then also in some amphibians, specifically the salamanders, what we see in them is they have their legs much more horizontally positioned out to the side, right? And so it more so looks like that they're basically like, it looks as though that they're crawling across the floor when they move, right? And so that's the more that's the way that the earliest tetrapods were moving, more so not like the more advanced way that we see in mammals. And so that's important to understand when it comes to understanding the evolution of the limbs in early tetrapods, because, you know, obviously it wouldn't really make much sense to go like right from like a fish to something that walks around in the type of way a dog does, because something like a dog has a much more advanced form of terrestrial movement, right? And so there obviously has to be a lot more intermediate. You can't just go directly from something that's like a fish to something with as advanced a form of movement of like a dog or horse or elephant. The earliest tetrapods were moving around in a fashion more similar to like salamanders and lizards, right? That's what's indicated by fossils. And as I covered on the other video, right, the earliest tetrapods, fossils indicate that the earliest tetrapods had more than 5 toes per foot, whereas generally in living tetrapods is most common to have 5 or less toes, generally not more than that. But that's different in the earliest tetrapods, right, that we find in the fossil record. And then also the differing parts of the what's now in our limbs first began as fins, right? We have fossils of fish that had phalanges in their fins, right? And the closest living relatives of tetrapods, the lungfish and the coelacanths, they already have primitive limbs. Their fins, one pair of fins that they have is primitive limbs, right? With homologs to the tetrapod humerus, radius, and ulna, and the muscles that move the fins for them are in the fins, whereas for most fish, they're at the base of the fin. And lungfish, because of that, along with the fact that they have true lungs, lungfish, they can spend extended periods of time on land, right? And so the human limbs are very much reducible. Also, even the front legs and feet are not fundamentally different from the back legs and feet for tetrapods, right? They use the same fundamental genetic instructions, so it didn't have to all be evolved from scratch. Same with the left limbs versus the right limbs, right? So in all of them, you see the same fundamental pattern of one bone, two smaller bones, little bones, and digits, whether it's the front limbs or the back limbs. And what allows for this goes all the way back to early bilaterians, which is a group that even includes things like insects. Early bilaterians evolved bilateral symmetry where the left side mirrors the right side, and they evolved body segmentation with the Hox code, the Hox genetic code, which is something used by most bilaterian creatures for like determining the positioning of differing body parts. And there's been some experiments that have helped shed light on how this works, such as the famous Drosophila fly experiment, where they showed that certain mutations can make this fly have its it could be born with its with legs on its head where its antennas are supposed to be, right? Because there are certain genes that determine the positioning of different body parts as well as the amount of them. And part of what helps in determining the positioning is the segmentation of the body that was evolved by early bilaterians. And so this same system is how the insects, for example, get all of their legs, and same for the arachnids, same for the horseshoe crabs. You know, the creature with the most legs of any living creature has over 1,000 legs, but it didn't have to evolve all of those from scratch because the same basic instructions can be used again and again and again thanks to body segmentation and the Hox code and bilateral symmetry, all of which go way back to early bilaterians. All right, that's all for now. See you guys.